Hi, this is Reagan Horton, and I'm with the Process Pioneers. We're going to be going through our project networking for our construction of a vessel for the Texas Park and Wildlife. So I am the project manager of the Process Pioneers, and then we have Abdurrafi Lasil, Daniel de la Pilima Lakini, Logan Ransom, Pranith Lingala, and Sarah Alden. A little bit of a background summary before we get started on the network diagram. We are using a 36-foot aluminum vessel with a single diesel engine and full cabin as our vessel for the Texas Park and Wildlife. We decided this was the optimal vessel for them in a previous presentation, and then we had the work breakdown structure associated with that. We are directly using that as our guidelines for the network diagram. The approach follows a structured methodology ensuring efficient sequencing of tasks from project and planning to completion. We're going to be using critical path analysis and our slack calculations to ensure that we find out what is the timely method in which the project can be completed given the following activities. Our approach to creating a network diagram is we had the work breakdown structure from a previous presentation. We took that to create our activities from the work packages there. We wanted to make sure we balanced the simplicity, but also have enough detail that would be necessary in the construction of a vessel. We use the critical path to identify which one of these activities would be detrimental to the project as a whole. If we were to delay it, it would delay the project. And then we also calculate the slack where we had a little bit of flexibility in our scheduling of these activities. To validate this, we used a variety of techniques from accuracy, both in the manual and the software-based checks. The major systems we covered in the previous presentation will also be here as the whole construction materials, the propulsion system, electrical system, freshwater system, sanitation system, navigation system, anchoring system, and the research system. Here's our activity table. This is going to be demonstrating what our activities are on each node. We have a small difference here from the previous slide where we separated the hull construction and the hull decking. We felt these were each two very significant work packages on their own, so we separated them into two separate nodes. And then finally, we have sea trials, which need to be completed before we can hand the vessel over. In order to calculate how much time each one of these are going to take, we have the optimistic, likely, and pessimistic time in days it's going to take to complete each task. And then we wanted to calculate what the expected time and the variance is. So for that, we're going to use our formula here. The activities follow the beta distribution. So we're going to be using the optimistic plus 4 times the most likely plus pessimistic, and then we're going to divide by 6, which is again in reference to that beta distribution. And then for the variance, we have the pessimistic minus the optimistic divided by 6, and that's going to be squared. And that is going to be giving our expected time and variance for each one of our nodes, and it's going to help calculate which one is going to be the predecessor and the successor for each one of our nodes. These are the network calculations we have for each one of our nodes. So the activity is going to be in the middle, and then the earliest start is going to be in the top left. The expected time is going to be represented by the TE, and the variance is going to be represented by the BAR. And then earliest finish is going to be in the top right, latest start, and latest finish. Now we got these variables by using the forward pass and the backward pass technique to calculate each one of them. And we'll be going over that in our network diagram. So here's our overall network diagram. This is just an overview of it. We have our 11 nodes here: the project planning, hull, propulsion, anchoring, electrical, sanitation, research, freshwater, navigation, hull decking, and sea trials. All of these are placed in order based on the previous table that has the predecessors for each one of these nodes. We use the forward pass and the backward pass to calculate what the earliest start and the earliest finish is for each one of these nodes. So out here we have the activity of project planning. It's going to be our first thing we're going to start with. We cannot start any earlier than 0, so our earliest start is going to be 0. We then add the expected time of 28 days, and then we have our earliest finish of 28 days. This earliest finish then becomes the earliest we could possibly start on the hull, which is that 28 days. Then it's going to take us that 14 of the expected time, then that becomes the earliest we can finish is the 38 days. Then this transfers over into the propulsion, which is going to be the earliest we can start is 38 days. This follows throughout our entire diagram here until we get to the very end where our earliest we can finish is 172, which means the earliest we can start on the final node, the final activity, is going to be 172. We add the 21 days, and that is the earliest we can finish our entire project, is going to be 193 days after we start our project planning. Subsequently, we also do the backward pass to find using the latest finish and the latest start. This also helps us create our critical path. We go through here, we have the 264. It's going to take us, it's going to be the latest we can start is going to be minus that expected time of 243. So the latest we can start then becomes the latest we can finish over here on the whole decking. We subtract the 21, it becomes the latest we can start here of 222, and then we pass it out into the web here of all the nodes. This is just an overall overview of our network diagram. We will then be going into each section individually. Looking at the beginning here, we have the project planning and the whole. The project planning must take place before anything else because we must know what we're going to actually be constructing and how it's going to look on our overall vessel. We have to know what we're planning for before we can even start to plan out what the systems are and how long each one of them is going to take. So that one directly ties into the whole. The whole must be completed before anything else because we need to attach our systems to something. So here we have a diagram of an aluminum hull being built. This must be down as a base before we can get into our systems that splinter off of it. So once again, we're starting here at our earliest start is 0. Our expected finish 28 days, so we're going to add that as our earliest finish. Our latest start is 0. Variance is very small at 0.11, so our latest finish is 30. We're going to then transfer over into the hull, and then our earliest start is going to be 28 days directly from the earliest finish, and then we're going to do expected time of 14.5. So the earliest this can finish is 38 days. Latest this can start is 30 days. Plus the 14, we get to 51. And then our variance is going to be 3.36. So that is going to be our beginning of the diagram. And then we'll move on to the middle. So here we have the middle part of our diagram. This is where it really starts to form a web. We have in the previous slide here, we have the hull. And then we go into this part of the diagram here where it starts to splinter off. From there, we have propulsion, anchoring, electrical, and sanitation. And as we can see here, electrical, once it's completed, it then needs to go into research, freshwater, and navigation. This makes sense because in order to have all of our systems operate, we need to make sure we have electricity on the vessel beforehand. Meanwhile, these are all self-sustaining. They can all go and be completed and not affect any of these nodes here. So looking in here, we have the propulsion, we have the early start of 38 days, and then it's going to be one of our longer activities of an expected time of 78 days, a late start of 51, an early finish of 108, and a late finish of 142. Anchoring, 108, going to be a shorter activity, so it's going to be an expected time of 9 days. Earliest finish is going to be 119. Late start of 142, very small variance here, and late finish of 152. Electrical, earliest we can start, right, based off of the hull, is going to be the earliest we can start. Is associated with the earliest we can finish off of the hull activity. We then add the 20 days of expected time, and we have the 52 is the earliest we can finish. And then this ties into our research and our freshwater. And then our latest we can start is a 51. We add the expected time of 20 days into the latest finish of 79. Then this transfers over into sanitation, and sanitation again is going off of the hull, and it has a early start of 142 and an early finish of 151. This is the highest one of those, so that's going to be the constraining earliest we can start on the next activity, which is hull decking, which we'll go over in the next slide. And then the late start is 207. We have the variance at 1, and then the 10 days, and we have the 222 here. So that's going to be the latest we can actually start our hull decking in the next slide. So this is just a look at our middle part of the diagram where it starts to splinter off. Here we are at the end. This is again what we talked about where we separated the hull decking and the hull construction. We felt that each one of those activities was significant enough to where we could separate them in their own activities and it wouldn't be excessive. We also felt like it belonged at the end of the construction of the vessel because we want all of the systems in place before we put the deck down on top of it and it's ready for commercial use. We're ready to get some people on the vessel to use it. So the earliest this can start and the latest this can start are directly tied to the sanitation, which is going to be the one that has the earliest finish and the latest finishes that are the highest, and it directly correlates to that. So it's a latest it can finish is 222, so the latest this can start is the 222, and the latest it can, or the earliest it can finish is a 151. So that's why we get that number. And we have the 21, and we get the 172 for the earliest finish. We have a variance of 2.77, and then we have a latest finish of 243. So we need all of our previous nodes to be completed before we can move on to the decking. Once we get to the decking, it's just onto the sea trials, our final step before we turn the vessel over and say that we are completed with it. And we have an early start of 172, going to be 21 days expected time, 193. Latest start is going to be a 243 with a variance of 2.78. And then the latest is going to finish, this is going to come back later, is our critical time of 264. So once we have our network diagram, we calculate our slack after we did the forward pass and the backward pass. We have the latest start minus the earliest start, which is going to calculate our slack. So project planning, that's the very beginning. We're not going to have any slack on that. The hull is our first node off of that, and it's going to have 2. And then we're going to have propulsion, electrical, sanitation. And as we can see here, that the sanitation, hull decking, and sea trials actually have a fair amount of slack, which is good. That means we can perform these tasks and have a little bit of a delay without it affecting the project as a whole. From our network diagram, we concluded that there was a critical time of 264. This is the latest it can take to complete the project without it being late. And the critical path is going to go from the project planning, hull, propulsion, navigation, hull decking, and the sea trials. As we stated, here's the critical path here. It goes from the project planning into the hull, the propulsion, and then the navigation to the hull decking, and finally the sea trials. We have illustrated here with the red line. This is items on this critical path. They cannot be delayed. If they are delayed, we know that the project as a whole will be delayed, whereas the anchoring, electrical, sanitation, freshwater, and research can actually experience a delay and not delay the project as a whole.